So this is joint work with some people from EPFL. So Artur Yazanov is my student. Dmitry is here. Also Ilan Newman from Haifa. And I also, there's this an independent paper by Pavel Rubesh. I also want to mention some of his results. I hope it's okay. You can do like this signal. So he kind of inadvertently did something that complemented our paper. Okay, so I want to start by asking you a question. So suppose I have some Boolean function, I'm interested in its circuit complexity, and let's say it's a kind of a mildly hard function. So the circuit complexity is like exponential in root n. How do we feel about this function? It's as complexity theorists, you know, it's mildly hard, so we're not super excited. Could be like 2 to the n is what we would prefer.
So if you prove the upper bound or the lower bound. If you prove the upper bound, we're not excited. Prove the lower bound, we are excited.
Let's say this is the circuit complexity. So you can't. This is the big number.
So somebody, you've told us explicitly what this function is. That's a.
Sorry to disappoint the person. But let me ask you, like, okay, so it's not super hard, but would I still be able to kind of find the hard part of the function? So would it be possible for me to find some set of inputs of, you know, roughly the same size as the complexity, such that on this subset of inputs, the function is kind of maximally hard. So it has the original complexity roughly, it's preserved, even if I'm just looking at a small subset of inputs. So it's like on this subset, the best you can do is just write down its truth table.
What do you mean? What is notation? F restricted to S. Oh, it's inputs. It's not. God, sorry.
Yeah. So this you could say it's it's only kind of defined on a subset of the Boolean cube. I don't. You propose a circuit. I don't care what the circuit does outside the set, but as long as on the set S you compute the function. Has anybody seen anything like this before? Finding like a hard part of a function? You could also assume that. Okay.
Hardcore.
Yeah, so I guess that's what I'm alluding to here. This hardcore lemma theorem that sort of says that this happens for every function. And let me actually, it's a weak version of the lemma. Let me actually prove it very quickly. It might be informative. So okay, so start with this complexity for the function. So the first step is to say, well, the circuit could be, I could even allow it to be a randomized circuit. I mean, there's no difference between a randomized circuit and deterministic circuit. Edelman says they have the same power. So even randomized circuits will have this complexity. But then by Yau's minimax, you know, randomized computation cannot compute this with high probability. There's some hard distribution. So some hard distribution over here, which is such that any circuit of this complexity, now a deterministic circuit, is going to fail to compute that function on this distribution. With, you know, it's going to have like constantly many errors. So how do I get my set S? I mean, I don't know anything else about the distribution except to know that weakness is the hardness, and I want a set that's sparse. So all I do is I just sample independently from the distribution this many points. And I claim that that's my set. So why? I mean, if I sample 1 point from the distribution, so I'm looking at one typical point. Well, on this point, let's say 1/3 of all my candidate circuits, so circuits of this size, they're going to make a mistake. 1/3 of them are going to fail on this point. So I include this point in my set S, I'm already like chucked out 1/3 of all possible circuits. So then I take another sample. Okay, now 1/3 of the remaining circuits are going to make a mistake on this point. Okay, you kind of repeat this, take, well, this many samples, and at the end you've exhausted your whole pool of candidate circuits. So this is all classical. Just wanted to put it up as motivation. I don't call this hardness condensation yet. I would just say that the hardness is concentrated on this set. We don't know too much about the sets. Be very complicated. Okay. Then let me give you another example. So let's do graph theory. Let's say the chromatic number of a graph is a kind of a complexity measure of a graph. And suppose I have a graph whose complexity is k. Well, can I somehow, again, like witness it locally? Can I find a small subgraph that already has the chromatic number k? So what do you think? Like, let's say I'm looking for a roughly k vertices in the graph.
No.
Why not?
Just
Cycle.
exactly.
Okay, I guess we could generalize this to any case. Cycle is an example, but even
Large curves, yeah.
yeah, like you can have graph with obviously large chromatic number, but also way larger girth. So every kind of subgraph is just a two-colorable forest. So we couldn't find a concentrated hardness for a graph and a chromatic number. Okay, third quiz. What if I look at the vertex cover number of a graph? Can I now find a small subset of a graph? Let me allow you, something that depends on k.
Just gonna line sections.
Okay. So stuff like this people study in fixed parameter tractability. So I'm not an expert, but what you sort of do if you want to solve this problem, you want to find this like part of the graph that just depends on the size of the parameter k and brute force over that set. So, okay, so vertex cover number kind of can be witnessed locally. Okay, so we want to study this sort of a question for different models of computation. Let's start with query complexity, my favorite. So now suppose I'm given a Boolean function and it has some decision tree complexity k. So any decision tree that queries the bits of the function needs at least k many queries to compute it. And I ask, well, does this query complexity can I witness by passing to a sort of a sparse subset of inputs? So it's like for the circuits, I'm looking for some subset of input bits that's sort of, exponential in the complexity parameter, such that already this kind of restricted function has the same query complexity. So what do people think? Is it possible to replace the Boolean cube with something a lot sparser, where the query complexity is still preserved?
Why wouldn't the minimax argument work again?
Okay, so you could try to do, say, replicate that argument. The problem here is that deterministic and randomized query complexities are not the same for F. So randomization does help.
But up to a polynomial factor.
Okay, so maybe up to polynomial factors this could work, but I want linear in K. So let me remind you, what does it mean to have query complexity K? Or a lower bound of K? It means there's an adversary strategy that can answer queries for K many steps without fixing the value of the function. So I guess I would like a set where you can still do this. You can still answer like fixed bits in any way you like, at least for K steps.
You take an input from each leaf?
Say again?
Would you just take an input from each leaf?
So you're saying, okay, so I guess that would be, I'm not sure if the quantifiers are correct. You would say for every proposed tree, there's a, I want one set where every shallow decision tree fails. Again, we were not moving forward until I get the right answer. So again, like my adversary strategy is, you get the query bits, I get to fix them for at least K many steps. Like give me a sparse set S that will support such a, carrying out such a fixing strategy.
And I can play against the adversary.
Sorry?
Epsilon bias.
Okay, so I call them like K-wise independent sets. So they take the support of a K-wise independent distribution. So it's a set that, you know, whenever you look at any k bits and you kind of marginalize the set there, I mean, I guess we did it on the previous talk, you can find any possible pattern of k bits. Right. And it turns out that you can find sparse subs. Sets, in fact, there can be a fine subspaces.
So it's not linear. Sorry, is this like BC dimension? Would it be another way of saying it?
Yeah.
Well, I want for any subset of k bits to have all the possible patterns.
You don't quite get.
Why do you need a lot? Or one suffices.
Yeah,
Sorry?
Why do you need a lot? If you just have,
I guess it depends how the adversary answers these queries.
So Mika.
Yeah.
Are you okay with n to the k? Like, you know, that theta tilde hides log small n?
Yeah, it's really n to the k. So. But okay, so it's still quite, so this is a hardcore set for query complexity. And we, you know, it's kind of constructive as well. So that's nice, but I want to do a little bit more with it and people have in the past. So you can actually implement this k-wise independent set through just, you know, as an affine subspace. So you can actually set it up that you can replace the function you start with. Okay, so it has n variables, and let's say it has this decision tree complexity. Okay, and well, you can sort of, you know, use this k-wise independent idea to compose that function with a bunch of parity gates fixed to a new set of inputs. So here you have roughly k variables. So, you know, different settings for the k variables, they kind of generate this k-wise independent hardcore set for the function. And you get additional properties like the degree here above is bounded, it's small. So you don't actually, by doing this composition, you actually don't destroy the query complexity of the original function. Each of these bits inputs left, you still can compute by querying only like few of the new variables. So this is what we call condensing hardness. So we've started with many variables. We have some sort of construction that replaces that function with another function of fewer variables where the query complexity is still maintained. So I obtained this function with maximal possible query complexity. So I guess this was first introduced by Rasper in the context of proof complexity. Loads of work using this construction in proof complexity, and maybe, I mean, I heard some rumors that maybe we get more later this week.
No, this.
It's negative.
Got it.
I heard you use projections. So is that,
Projections, yes.
Yeah.
Clever.
which is like the same, but you don't have parity gates, you just reroute. There's parities of one variable, so it still lies within. Okay, so what are we doing in our work is why not do something simpler? So now what is the simplest operation to reduce the number of variables to a function? It's one way. Another is just, well, fix some of the variables to bits. So now, in other words, I'm kind of looking for this hardcore set. That's a subcube. So let me just like put down formally what I'm asking you to do. So I start with query complexity k, and I want to find this partial assignment to input variables that leaves free k variables, sets all the other bits, such that, you know, the query complexity is affected. You still have roughly k complexity remaining. Maybe it's fair to say, why are we doing this if this expander construction does work? And well, I think it's still a kind of a nice question to ask, like whether you can do even a simpler style of hardness condensation. Another motivation is that sometimes you can't afford to build gadgets, and you actually have one application where we don't really know how to obtain it using gadgets, so we just have to use this like a restriction. Okay, so let me demonstrate this question a little bit. Let's look at an example. Yeah.
But you want the fixed variable, so you wouldn't be happy with the substitutions.
No, just, you know, we're fixing for now. Yeah. So let's look at this example function. It's one of the classical ones I've found a reference from the 70s. So what is this function? So it's defined for a kind of a complete graph. You get an input bit for each of the edges of a complete graph. And the input bit for that edge, it determines what direction should I assign to that edge. So the input defines an orientation of the complete graph. And the function outputs 1 if there's a sink in the graph. So there's some node such that all its adjacent edges are pointing to it. So there's could be only one sink in this example. There is this red one. Okay, so it's not hard to show that the query complexity of this function is linear in n. So that's
Randomized query complexity?
deterministic.
Okay, so
That's what I'm discussing. So, okay, number of variables is quadratic in n, but the complexity itself is n. So can we solve, can we condense hardness by fixing input bits for this function? Any ideas? I want to fix some of the input bits of this function, leave roughly n unfixed, such that now I get this function on n variables and it still has query complexity n. Yeah.
And so if we fix all the inner edges and then just on the cycle, it should be. No, this it doesn't work. Sorry.
So what's an inner edge? I think you're going in the right direction, actually.
But I was thinking if I don't have a complete graph, if I just have a cycle, then it's still hard to determine if whether one of the.
it's got to alternate directions on the cycle or something like that.
Yeah. So okay. So here's maybe another way of saying it. Suppose like all of these guys here.
Yeah.
Light on a cycle. So, and actually it's true of the gray orientation I've written. I could, the answer is I could fix all those edges that are gray in my picture. And what I leave active are just the red edges. And it would still be difficult to decide if that red node is a sink. You still have to kind of query all the adjacent edges to make sure that they're all pointing to that edge, that node. And by the way we fix the rest of the variables, we made sure there can't be any other sinks because they all have at least one incoming, one outgoing edge already amongst the gray fixed variables. Okay, so this is an example where we could condense hardness.
Did we condense sink to or now?
Yeah, so I kind of identified a or as a sub-function, you could say. Another way I would say that what we did is we kind of condensed to the sensitivity of the function. So, you can generalize this example to show I can always condense to the sensitivity of a function. So it's like maximum over inputs of the kind of the largest or function or and function you can fit in that sort of corner of the Boolean cube. I also claim we can condense to degree. So my Boolean function has some degree k. I can write it as a multilinear polynomial degree k. Then I can condense to that degree. So I can set restrict all but k variables such that the query complexity is still k. How do I do that? Okay, so I have a multilinear polynomial, so it's degree k. So there are some monomials, k variables.
Maximum term and
Yeah, just pick a
maximum
maximum.
term and fix an assignment so that you don't kill it.
Yeah,
Oh,
okay. Everybody at the same time. So yeah, it's also easy. So one of my main results is you can't do this in general. So there are some functions where you cannot condense to the query complexity. And already from this slide, like knowing we can do it for sensitivity and degree means if you have a counterexample, something where you can't condense to the query complexity, the function or counterexample function necessarily needs to be one that separates, like the query complexity is both larger than sensitivity and degree. And okay, in the literature, there are such functions. We can actually use one of those existing functions off the shelf to show this counterexample. So yeah, so we exhibit some k-query function such that no matter how you try to restrict it to k variables, the query complexity will drop polynomially. So yeah, it could not. It's a negative result. You cannot, in general, condense query complexity. I should say, where does this function example come from? I don't have time to discuss it, but it uses something called cheat sheets. It's a construction in query complexity. I just want to say, when I kind of proposed this to my co-author, Ilan Newman, so he's an old god. He's writing a textbook on query complexity. So he's like an expert. I don't know if the textbook will ever come out. They've been working on it for some years. But in any way, so he was surprised. Wait. Cheat sheets, don't they just allow you to prove some like quantum separations? And it's true that they were introduced in that context. But maybe the takeaway here is that it has all sort of interesting classical implications, and I encourage you to read up on cheat sheets. It's I haven't seen them used in proof complexity yet, but yeah, it's a tool that's very powerful. Okay, so you could not condense query complexity in general. Now I could ask the same question about communication complexity. Suppose I had a two-player function. So I think of it as this binary boolean matrix. Say it has deterministic communication complexity k. Well, can I condense? So now the natural way of fixing bits or restricting the input domain is to pick a submatrix. That's my format for trying to restrict the function. So the question now is, if the complexity is k, can I find a submatrix, which is k bits, so of size 2 to the k by 2 to the k, such that when I restrict to the submatrix, the communication complexity stays roughly the same. Again, found this submatrix with nearly maximal possible communication complexity. Okay, so in short, this is open. Don't know whether you can always do this. So here, Ruben showed you can do something. Maybe you can't condense quite to communication complexity k, but root k is okay. So if you plug root k all over here, it's true. And what's really interesting about this is that this claim is a kind of a consequence of the log-rank conjecture. So I claim that rank can be condensed losslessly. If you have a rank k matrix, it has a k by k submatrix of rank k. So rank condenses. Should deterministic complexity also condense? Well, yes, if you believe the log-rank conjecture, both should condense, but maybe with a polynomial loss. My proof shows that yes, you can actually, at least with polynomial loss, you can condense. But I suspect you cannot losslessly condense. I suspect you can't do linear in k. But I can't disprove this conjecture. In fact, what we've done a lot is we've tried to disprove or construct weird separating examples in communication complexity by first solving the query analog and then lifting. And try to do it here. We have a counterexample for query complexity, right? But lifting turns out it kind of fails, and then we have a side result saying that you can't. Every lifted function does condense, so it does not give a counterexample to it. Yeah. Okay, this is still open. Okay, we also study randomized communication. It's very easy. You can look at the greater than function to see that you can't condense randomized communication. So I should probably wrap up. So there's a bunch of open problems. So, okay, you could try to improve our counterexample to condensing query complexity quantitatively, like find a bigger gap. There are other query complexity measures or Boolean function measures that we don't know if they condense. it's like this partition number or unambiguous certificate complexity is interesting because for communication, Froube showed you can condense the communication analog of unambiguous certificates. We don't know if you can do that in query complexity. I also wondered if you go back to this line of work with this expander composition with XORs, whether you could condense randomized query complexity. So you can certainly get through the argument from the first slide, you can certainly get like a hardcore set. But I don't know if you can like make it in like generate it through an expander. So I haven't thought a lot about it, but I think it's interesting. I suspect you can't do it, but it would be nice to prove it. Then there's a kind of an open-ended direction to look at. Well, again, my first slide about finding hardcore sets for circuits. Well, could you do something to condense hardness for circuits, like actually reduce the number of variables? Maybe it's too good to be true. Like you look at any area of circuit complexity, it's just one example. The best depth-free lower bounds we have are merely mildly exponential. If you had some magical way to condense that and get maximal lower bounds, you'd be, that would be a breakthrough. So, okay, maybe I don't know, it's a lot to ask to do this in full generality. Okay, Andy.
A stupid question. For query complexity, what happens for a random function?
Yeah, I guess its query complexity is n, and there's nothing to condense anymore.
Nothing to condense, because it will be why?
So I guess condensing only makes sense for functions whose complexity is less than the number of variables. And there's something you can do to reduce the number of variables. But if you start with a maximally hard function, okay, that's already maximally hard. Don't need.
Okay, condensing. Okay.
So you can't condense decision tree complexity perfectly, but we know that you can up to a polynomial factor. Can you do any better than what you get from the rank from like can you get anything?
I mean, you can always condense to degree and sensitivity, and those have.
So those would be off by a square, but I guess.
Yeah, I think, or cubed.
Or something,
Yeah, I think cubed is, yeah.
But that's the best you know.
That's the best we know.
I see. And the lower bound, like it's.
Our example only goes from k to power 1.75, so it doesn't even.
Oh yeah, right. Okay. Cool. Thanks.
I guess you could also look at condensing decision tree size, right? Have you thought about that?
Decision tree size. Well, okay, so depth and size, I guess, are related by some gadget construction. So I think you can also kind of use our counterexamples to disprove it for size. If you're, again, restricting or fixing input bits.
Yeah, I guess what do you mean by if it's about restricting variables, yes, but maybe there are other ways which you can.
Yeah. Questions?
One-way communication complexity.
Good open problem. I haven't thought about it.
Maybe it will be the first step, or maybe the last step towards the second one.
Question, answer.
Okay, thank you.